Simone Winkler, talking about vibroacoustics and MRI.
Good morning. Thanks for the invitation. I'm going to be talking about acoustics, which is a topic that's a little bit rare. So I have interest within Genrix and GE to declare. We've already heard a little bit about different gradients, so I'm not going to go into much detail, but basically we have the built-in body gradient that's versatile, and then the head gradient insert coils with higher performance at the trade-off of some of the linear region. These are attractive, but we also wonder if they're any louder. We have to be careful in terms of safety. So why are MRI scanners actually loud? Most of you probably know this, but very quickly the gradient conductors have currents running on them, and because they're in a strong magnetic field, there's a Lorentz force that is induced, and because these currents are time varying, you now get a vibration. And so now the gradient shell vibrates, and that means that you get a pressure change at the bore wall, which results in a sound wave. Now, these structural vibrations come in different modes, and basically the spectrum is then a weighted sum of these different vibrational modes. And then what happens is that the shell presses on the air in the bore and causes this acoustic sound wave to form. Now, in terms of what has been done in acoustics, actually, it was kind of shocking when I started to work on this, not very much. These are pretty much all the papers I found. So early on, people tried some trial and error methods to reduce sound pressure levels. Later on, some analysis started, but computational power was still limited, so these were fairly basic. This one's analytical shell modes. This is just statistical energy analysis. And then some finite element analysis started, but it was still very limited. So here, really, computational power was good enough to start and analyze these things more realistically, and so I'm going to be talking about that a little more in detail. And what I like a lot is that after my work here, a lot of new stuff has come up, so that's exciting. So in terms of understanding what actually happens in terms of vibroacoustics, I have kind of come up with this hierarchy. Step A to C is to look at the gradient coil only without anything surrounding it, so no air, no scanner. And that kind of gives us an understanding of how things work. And then in step D, we add other things like the warm bore, the air around. And as you can see, this is a lot simpler than what's actually happening. So the simulation compared to the experiment has a pretty good fit, I would say. But we also need to look at this to actually understand things. And literature before I started made it somewhere until here, approximately. So it's good that we now have computational power to look into more detail. So step A to C are outlined here in a summary. There's going to be more details, so don't feel overwhelmed. First of all, you can look at the eigenmodes. So there are two types. One is the acoustic eigenmode, which is basically the sound waves that can resonate in this air cavity inside the gradient coil. And the structural eigenmodes are basically the eigenmodes that form with this structural vibration of the epoxy shell. And you can make a list of all these eigenmodes with their frequencies. And then obviously the sound pressure levels are excited by the Lorentz forces. So first of all, you have to look at what they look like. And these then yield a spatial pattern of excitation. Then you can run a harmonic analysis and you get a spectrum like this. So I'll show more of that later. So if we look at the step A, which is the eigenmode analysis, you can identify the acoustic eigenmodes. We use soft boundary conditions here, and then the eigenmodes of the epoxy gradient shell with simply supported boundary conditions. So there's an example of the 112 mode. One is the radial mode number, so variations from in the radial direction. The second index is the circumferential variation, so that's 1 also in this example, and the axial variation here is 2. So that's kind of how these are identified. Now, if you do that, you get a big list of all kinds of eigenmodes, which is a bit overwhelming, but it was very instructive. And so with that list, you can also identify modes that can couple. So what that means is that these modes have the same frequency and also the same mode shape. So in gray, you have some here that have the potential to couple. And you can also visualize this a little better. So if you have the acoustic eigenmodes in gray and the structural eigenmodes in red, those that overlap have potential to couple. And these are important because they can get really loud because energy is exchanged from the structural vibration to the acoustic sound pressure propagation and in return back and forth. So our step B is the Lorentz force excitation. So if, for example, you have 50 ampere of gradient current in a 3T scanner, you get a maximum of 150, that should be Newton per meter. And what's really important here is the radial component because that is what in the end excites the sound pressure. So this is the X gradient, the Y gradient, and the Z gradient and its components. And we can already see some things happening here. So for example, in the X and Y coils, we can see that the excitation has a circumferential variation of 1 here. So we kind of foresee that modes with odd orders of circumferential variations are going to be excited. And for the Z coil, we don't have any variation in circumferential direction. So we think that basically the 0th order of modes are going to be excited. So now if you look at the harmonic analysis of the standalone coil, you get these spectra. So green is the Z coil and red is X and Y. And this is really what happens. So we said before that these modes are excited. I'm going to talk about that a little later, but we see that confirmed. So each of these peaks corresponds to one of the acoustic resonant modes. So this is the sound pressure level spectrum. And then here you see the vibrational spectrum with the accelerations. And what you can infer is that really these resonances that are happening here aren't really showing up here. So what really matters more, it seems, is that the acoustic resonances show up. So in a way, we can decouple a little bit. So we think that the average sound pressure level is determined more by the vibrational response, and the spectral shape is more determined by the geometry of the air cavity. So as I said before, because of this radial force pattern, we think that only odd modes are excited by X and Y gradients, and you can see that happening here in the red curve. And the same for the Z gradient. We have the 0th order modes here showing up. So I mentioned coupling before. This is when the mode shapes are the same at the same frequency, and that's kind of a big problem because things can get really loud. So I played around a little bit here, and you can see here, this is the acceleration or vibrational response. There is this red curve that shows coupling. So you can see this little spike here, and that results in a very loud operation in terms of acoustics. So a little bit happens in the blue curve here too, but it's already lower. So this is something when you design a gradient coil, you might want to look into these coupling effects that can get important. So now we arrive at step D, which is actually the more realistic analysis. Step A to C was kind of more important to understand what's really going on, but step D actually corresponds to practice more. So we, in addition to the standalone coil, we added the warm bore as a hard acoustic boundary. We had the patient bridge. There's no displacement here, so the coil is fixed. You can also add more things, but depends on how much time you want to spend on solving these things. So we also added surrounding air with an infinite half space of air using perfectly matched layers. And this was going to be a video, but my slides crashed. So what you would see here is that, there's a mix of resonance, and then, these waves really travel outside into the air, which is an important aspect that changes things a lot. So these new features include the accurate wire patterns and all these other things that I mentioned. Lorentz damping is something I will explain in a little bit. So the results of this were actually really nice. I didn't believe it at first, but it was a fairly nice agreement between simulation and experiment. The Z gradient is a little bit different, but I think that's due to the fact that this has hollow copper conductors, so you might want to introduce a little bit more detail here. There's probably a little more room for improvement for vibrational response. You can probably add the scanner and other important features, but it seems as though they're not so important for the final sound pressure levels. So some observations also in terms of comparing body to head gradient inserts in terms of acoustics. So the observations we saw was already only certain modes are excited by this specific head gradient, and in the body gradient we analyzed, we had more modes. And what it does is actually it ends up being louder because more modes are excited. So the average was higher than the body gradient. And in addition, what we also observe is that in the head gradient insert, some of these modes are shifted to higher frequencies because the gradient is smaller. So for example, the 011 mode here is actually at a lot higher frequency for the head gradient insert. So if you look at the band of frequency of interest for RF pulses, you might even shift some of these modes outside the spectrum and can operate a little more quietly. So short is good. This is the experiment. It's not really reflecting that the body gradient is louder, but the body gradient had acoustic absorbent material that we can't take out because it's built in. So, take it with a grain of salt, but I wanted to show the measurements still. Now, the Lorentz damping that I mentioned before is actually something I found while I simulated these gradients. And what happens here is that you have obviously these gradient conductors with a current running on them in the static magnetic field, causing a Lorentz force, as we mentioned. Now these move because they're vibrating. So they have a velocity v. And what that means is that you induce a counter current, proportional to this velocity v. And so the total current is reduced by this counter current. I'm sorry, I did it. And so now you have a total force that removes this countercurrent component. And the total force, if you write that explicitly for field strength dependence, seems to be proportional to the square of the field strength, which I found very interesting. So if you write down the equation of motion, you have this term here. And what that does really is it dampens your vibrational response quite a bit. And that's actually an interesting result, because now if you look at field dependence, you can analyze the situation without this term included, and then you can add the damping term, and suddenly this situation of having 10.8 dB more when you move from 3 Tesla to 10.5 Tesla is not showing up here anymore. So they're fairly similar. So now I know in 2 presentations ago we saw something different. So I think there are some open questions, but at least it's food for thought. Then one more observation here is that there's a coupled resonance, and that one does not really observe the linearity here. So we also thought of some strategies for reduction of sound pressure levels. We didn't really do very much, but there are some nice ideas, so I want to show those. So first of all, we thought that obviously stiffer materials lead to lower vibration because of their lower Young's modulus. This is a bit of a chaotic curve, but I still wanted to show it. So if you look at different Young's moduli for the epoxy shells, so stiffer gradient shells, the accelerations here are very different, but these resonances don't really show up at the top in the acoustic spectrum, which is important to note. So we can sort of decouple these effects. So we think that the average sound pressure level is determined more or less by the stiffness, and then the spectral shape is determined by the shape of the air bore of the gradient. So what we did was we added ceramic liners in simulation. You can see that here. The 20 millimeter liner that's shown here resulted in about 17 dB reduction, and we can also see, I think the higher frequency band was attenuated more than the lower frequency band, so those are also important findings. Then we simulated some more. If you also add ceramic on the outside, you can get to even further reduction, which was on the order of 30 dB. We didn't actually build this. It's kind of hard to do. So you have to pot your whole gradient coil into ceramic. I don't know if you want to do that easily. So another concept was kind of cute. So we thought that this was a video too, which is kind of a shame because it illustrates things so nicely. But if you just look at the standalone gradient coil, basically the energy in here is mostly resonating, so it pulsates. Now, if you actually find a way to get all that energy out of the gradient coil, then it won't be so loud in there. So it's a little bit like an antenna or a horn where you can, get your acoustic energy on the outside. In a way, it's impedance matching between the impedance on the inside and the free space impedance on the outside. It wasn't a dramatic effect, but we got a little bit of a reduction, so a few dB. We also added a foam end cap. So I think there's room for improvement, but it was kind of a nice idea. Yeah, and then I guess this is not really acoustics, but I wanted to show one last slide on gradient cooling because it's also important for safety. This was supposed to be an image of what happens at 30 seconds, but I think that got lost. So we had a video here, but it crashed. So what you can see is how cooling basically affects the temperature inside and outside of the gradient. And we looked at, for example, here, if the cooling fails, the flow is on in this case. We have, on the order of 25 degrees or so. But when the flow is off, suddenly you get to 60 degrees Celsius, and that could be, bad for the coil, but also for the patient. So this is something that you can analyze in simulation very well also. So it's maybe important to mention in this safety talk. So yeah, in conclusion, I think we understood that vibroacoustics are very complex. There hasn't much work been done before. The standalone analysis can teach us a lot of things, but it doesn't really include some of the things, and we noted that those are really important. So the realistic analysis is made possible by modern methods, and those are a lot more realistic. Lorentz damping is something we kind of found while working on this, so we included it. We think that these new tools can now offer a lot of ways to reduce sound pressure levels. And I think, in addition, we can also look at gradient cooling, which is important for safety. So thank you for listening. Yeah.
Yeah, thank you very much for sharing these very interesting results. Any questions from the audience?
Sorry, I didn't really understand. You said one of your statements was that the baseline sound pressure is determined by the resonant modes in the gradient coil, and that these individual little resonances, well, they can be quite high, but the peaks in the spectra are the acoustic modes. So I would assume if you modify the interface, as you suggested, of the two, that you can affect the coupling between these two. And in a way, I would always assume that should always be possible in the gradient design, so get rid of this partially disastrous coupling effect. But you also said with this ceramic bore liner or gradient liner, which you suggested, that you can get the total level down by a quite impressive amount. So how does that relate? Is this doing more than affecting the coupling between the structural and the acoustics, or what is the effect of the ceramic there?
I think those are two different effects. I mean, the coupling, you have to be careful because now if you add a ceramic liner, you'll have different resonant modes for the structural vibration, so you still have to take those into account. But I think overall, because the coil is now stiffer, it will displace less, and therefore you will get less sound pressure levels. So the coupling, you'll still have to analyze separately.
So the
that
basic
question.
effect is not the coupling of those, but really making the whole gradient coil stiffer, actually by what means ever. That would be the major effect to bring
Right.
the pressure down.
Yeah, and the coupling you have to look at separately, because that could still happen.